Today you will learn how to multiply conformable matrices and understand and use the laws of matrix arithmetic. Let's take a look at how to multiply matrices. To multiply two matrices, you need to multiply the rows in the first matrix by the columns in the second. We take the first row of the first matrix and the column in the second matrix and we multiply the elements together. Here we are multiplying 1 by 3, so that is the first element in the first row of the first matrix, by 3, which is the first element in the first column of the second matrix. We then add on the second element in that row by the second element in that column. We work out the calculation, 1 times 3 plus 2 times 4, that gives us 11. Then we do the same thing again, but with the second row in that first matrix. So we multiply the first term in that second row by 3, the first term in the second matrix, minus 1 multiplied by 3. And then we add on that last element, 0, multiplied by 4. Then we work out that answer. Minus 1 times by 3 plus 0 multiplied by 4 is minus 3. Now another thing to note here is the order of each of those matrices that we started with. So we started with a 2 by 2 matrix and we multiplied it by a 2 by 1 matrix, and we will take a look at why this is important very shortly, but just notice for now that these two numbers are the same. And then when we look at our solution, this is a 2 by 1 matrix, and this relates to these two numbers here. Let's take a look at a second example. I'm just going to show you how to check the size that the answer should be again. So if we have a 2 by 2 matrix multiplied by a 2 by 2 matrix, we know we can multiply them because these two here are the same, and the end 2 will tell us the size of the matrix for our solution, so we know what size to draw this. I'm going to make this a little bit bigger to show you the steps of the working out. And what I like to do is separate my rows in my first matrix with a line and my columns in my second matrix so I don't make any mistakes as I write these down. And then let me show you the working out from here. So I'm going to multiply 1 by 5 and 2 by 3. So 1 times 5 plus 2 times 3. That's the first element in my matrix. And then I'm going to do 1 multiplied by minus 2 and 2 multiplied by 1. I think I might just rub that bit out there. So we have 1 multiplied by minus 2 plus 2 multiplied by 1. And then looking underneath, so we need to multiply minus 1 by 5 and 0 by 3. 1 minus 1 multiplied by 5 plus 0 multiplied by 3. And then finally, we're going to multiply minus 1 by minus 2 and 0 by 1. Minus 1 multiplied by minus 2 and 0 multiplied by 1. Not the best colour choice there. Let's close the bracket on that matrix and then we'll work out the solution. This leads us to 5 plus 6, which is 11, minus 2 plus 2, which is 0, minus 5 plus 0, which is minus 5, and oh, I can see that I have missed the plus sign out in between there, and 2 plus 0 is 2. Okay, so these are the notes for looking at when we can and can't multiply matrices together, because not all of them can. So if the number of the columns in the first matrix equals the number of the rows in the second matrix, then it is possible to multiply them. So let's have a look at an example. Matrix A has order 2 by 3 and matrix B has order 3 by 1. So if we wanted to work out AB, A multiplied by B, then we first check the order. So the order of A is 2 by 3, the order of B is 3 by 1. Because the 3's here, the ones that are next to each other, are equal, it means that we can multiply them. And then the numbers on the outside tell you the order that the answer should be, 2 by 1. Here are matrices A, B, C and D. Your job is to see which of the following from the grid are not possible and which are possible. If they are possible, see if you can work out the answer to them. Just as a little bit of help here, a little guidance. If we check the order first of all, so the order of A will be, we've got 2 rows and we have 3 columns. So this is a 2 by 3 matrix. B is a 2 by 1. C is a 1 by 2. And D is a 2 by 2. Remember, when you are multiplying, that is the columns of the first matrix and the rows of the second matrix that must equal for their order. Have a go now. I'm going to reveal the ones that are not possible. Okay, so this is removing all of those that are not possible, and it will leave us with the ones that are. Here are the solutions to the ones that are possible. Now we've taken a look at how to add and multiply matrices, we're going to take a look at the laws that these operations hold. Now it only makes sense if the dimensions of the matrices are suitable for these operations, and so we're going to look at matrices that have the same order. In the examples that I'm going to give, we're going to use matrices A, B and C, which have an order of 2 by 2, so they are all square matrices. Looking at the first law, the commutative law, this is to do with the order in which the operations are combined. So the addition law would be A plus B is equal to B plus A. Now this is true for all matrices where the matrices are of the same order. But generally speaking, it is not true for multiplication. So AB is not the same as BA. Now let's take a look at both of these examples using the matrices A and B from above. So we'll look at A plus B, which is on the left, and B plus A, which is on the right. And working this out, we have 2 plus 3, which is 5, minus 5 plus 4 is minus 1. 1 take 1 is 0, and 0 plus 2 is 2. And on the right hand side, 3 plus 2 is 5. 4 take away 5 is minus 1. Minus 1 plus 1 is 0, and 2 plus 0 is 2. So these two are the same, they give the same result. Let's take a look at how it doesn't generally work for multiplication. So again, on the left we've got AB, and on the right we have BA. So if we're going to multiply these together, I'm going to draw my lines in just to make it a little bit easier to see. Okay, so let's take a look at this. 2 times 3 is 6, Minus 5 times minus 1 is 5, so 6 plus 5 is 11. 2 times 4 is 8. Minus 5 times 2 is minus 10. So 8 take 10 is 2. 1 times 3 is 3. 0 times minus 1 is 0. That gives us 3. 1 times 4 is 4. 0 times 2 is 0. So that gives us 4. And on the other side, drawing my lines again. So we have 3 times 2 is 6. 4 times 1 is 4. So 6 plus 4 is 10. 3 times minus 5 is minus 15. 4 times 0 is nothing. So that gives us minus 15. Minus 1 times 2 is minus 2. 2 times 1 is 2. Minus 2 plus 2 is 0. Minus 1 times minus 5 is 5. And 2 times nothing is nothing. That's 5 plus nothing, which is 5. So here we can see that AB is not equal to BA. Now there are some cases where AB is equal to BA, but generally speaking, this is not true. Let's take a look at the distributive law. So here we have A multiplied by B plus C is equal to AB plus AC. This is telling us that the multiplication of a number by a group of numbers is the same as doing each multiplication separately. Now we know this is true for numbers and for algebra, and it's also true for matrices. The same can be said if we have the A on the right hand side of the bracket B plus C. It's just you need to be careful with the right hand side there, as we already know that matrix multiplication in general is not commutative, so AB would not be the same as BA. I'm going to take a look at the top example of the law there, and just to see how that looks like as we're working through. So here we have matrix A on the outside of that bracket, and then down at the bottom there we have A multiplied by B plus A multiplied by C, and I'm going to work both of these out to show that they do indeed give you the same solution. So let's take a look at that first one. So our first step is to work out what is inside of that square bracket. So I'm going to rewrite the first matrix, and then let's work out what should be inside that second matrix. So 3 plus nothing is 3, 4 plus 6 is 10, minus 1 plus minus 3 is minus 4, and 2 plus minus 2 is 0. And then these two multiplied together. So let's have a line across and a line going down. So we have 2 times 3, so we have 6 plus 20 is 26, and 20 and nothing is 20. 3 for the next one, and 10 for the last. Now let's compare. So the first matrix, and we'll have plus the second matrix once we've worked out that multiplication. So I'm going to draw my lines going across for each one. So the first one then, 2 times 3, we have 6. 6 plus 5 is 11. And we have 8 minus 10 is minus 2. And then 3 and 4. And looking at the second one, we have 15. And we have 12 plus 10 is 22. And 0 there. 6 in that final spot. And if we add these two together, 11 plus 15 is 26. Minus 2 plus 22 is 20. 3 plus 0 is 3. And 4 plus 6 is 10. So we can see that the left-hand side is equal to the right-hand side, and this would always be the case. Now let's take a look at the associative law. Here, if we are trying to add together matrices A, B and C, it doesn't matter how we group them. So we can add A and B together first and then add C, or we can add B and C together first and then add A. Now this is also true for multiplication. If we want to multiply A, B and C together, we can multiply A and B together first and then multiply by C. Or we can multiply B and C together and then multiply by A. Now it's important that we still keep the order here of the A, B and C, otherwise this will not be true, as we know that matrices under multiplication are not commutative. Now if we take a look at the associative law for multiplication, I can show that this is true. So I'm just going to work through the numbers on this one just to show the left hand side is indeed equal to the right hand side. So let me pop the brackets around the things that I'm going to be working out first. And on the left hand side, I'm going to move through this pretty quickly. So if you wanted to have a go at yourself, then have a go now before I start writing this down. Okay, let's take a look. So the first two matrices here will give us 11, minus 2, 3 and 4. Then we multiplied by that second matrix, and this when multiplied together gives us 6, 70, minus 12 and 10. And if we look over on the other side, so I'm going to write that first matrix in first, and then the result of the second bracket. So the second one gives us minus 12 and 10, minus 6 and minus 10, which multiplying together gives us 6, 70, minus 12 and 10. Let's take a look at the zero matrix. This is a matrix that is made up entirely of zeros, and there are a couple of consequences when we apply the zero matrix under the operation of addition and multiplication that are interesting. So here we go under addition. A plus the zero matrix is equivalent to 0 plus the A matrix, which would just give us A. That means that A is remaining unchanged, and this can be quite important when you're looking at groups. Under multiplication, if we multiply A by 0 or 0 by A, it gives us the zero matrix. The identity matrix we know has a leading diagonal made of zeros, and under multiplication, A multiplied by the identity would be the same as I multiplied by A, and that just leaves us with the original matrix. Now these two are important. We've applied a matrix and an operation, and we've ended up with the same matrix as which we started with. And the final thing here is the multiplicative inverse. Now I'm just going to mention this, but we'll take a look at this in a future lesson. So here, provided that the inverse exists, and it doesn't always, so there are some rules around when it does and doesn't exist. But if we were to apply A inverse under multiplication to the matrix A, it would give us I, the identity matrix. And now that's in either order. So A times A inverse is the same as A inverse times by A. And that's another important result for matrices. Now let's take a look at the transpose of a matrix. So with addition, if we have A plus B all transposed, this is the same as A transposed plus B transposed. And for multiplication, A times B all transposed is the same as B transposed, A transposed. Again, be careful with the order when you're looking at the multiplication. Now, A transposed and B transposed are given here, so you can see that the rows and the columns have been swapped. So now let's take a look at how these work for this particular example. So here, just made a couple of steps forward so that I can work through this. So if I transpose the left-hand side there, that will give me 5 minus 1 and 0, 2. And on the right-hand side, 2 plus 3 is 5, 1 take 1 is 0, minus 5 plus 4 is minus 1, 0 plus 2 is 2. Now for the bottom one, so I've just worked out the product there of A and B, just again to make this a little bit more straightforward. And if we transpose this, this will give us 11 minus 2, 3, 4, and on the right hand side, this will give us 6 plus 5, which is 11, 3 plus nothing is 3, 8 take 10 is minus 2, and 4 plus 0 is 4. Let's take a look at this question. The matrices A and B are defined as below. Find in terms of T the matrix AB and deduce that there exists a value of T such that AB is a scalar multiple of the 3 by 3 identity matrix I. Now it seems pretty wordy, looks complicated, but actually is quite easy to work through. So the first step is to work out A multiplied by B. Now I'll go through just a couple of elements here just to show you where the values have come from. So if we take a look at that first element here, 32 minus 40, let's see where that value has come from. So we're taking the first row of A and the first column of B, and if we multiply these together, we have 1 times by 15, which is 15. 2 multiplied by minus 2 is minus 40. And 1 multiplied by 17 is 17. 15 plus 17 is 32. And then we've got the minus 40 at the end. For the next element, the 0 here, we need the second column of B, but we repeat the same process as we did for the first element there. So we have 1 multiplied by minus 4 is minus 4. 2 multiplied by 4 is 8. And 1 multiplied by minus 4 is minus 4. So that does indeed give us 0. And we continue on in the same way, filling in the 3 by 3 matrix there. Now, the next step is to try and solve this equation. So we have AB is equal to some scalar multiple of the identity matrix. So let's write that down. This is what we're looking to be able to solve. And it becomes a case of solving the equations by comparing the elements from the left-hand side and the right-hand side. Okay, so if we take that bottom element there, 28 minus 40, it must have a value of 0. So if we rearrange this, took the 40 across to the right-hand side, I'll write that down. So 28 minus 40 equals 0. That would give 28 being equal to 40. And therefore that would give us a value of T of being 7. And if we look at that final row there, we have 4. Now we're equating it to the 1, but don't forget that there's the scalar multiple of A just outside of that bracket. So that would give us 4 is equal to A. Please turn to page 146 and complete exercise 7B.